Okay, you guys, we're just going to do a quick overview of special quadrilaterals. This is just to bring up some vocabulary that we'll use throughout the year. However, we'll spend an entire unit / chapter investigating these in detail, doing proofs. So this is really just becoming familiar with a couple vocab words. So the big idea is quadrilateral is any four-sided polygon, right? So that means straight lines connected at their endpoints. It could be, any length straight lines, but four sides connected. That's a quadrilateral. And there's 7, we call them special quadrilaterals, that we're going to talk about, right? This usually has to do with either sides being parallel, or sides being congruent, angles being congruent, which in general, because there's 4 angles in a quadrilateral, if they're all 4 the same, then they're all 4 right angles. And again, that's something we'll discover and prove later on in the year. But that's really how we identify these 7 quadrilaterals, okay? You probably heard all or most of these terms, but we're just going to lay out definitions and then I'll do some practice problems. Okay, so a definition of a trapezoid is any four-sided figure with exactly 1 pair of parallel sides. Now, depending on your book, some books actually define this with at least 1 pair. So things that have 2 pairs, like this, well actually that's impossible. Because they're saying this side is parallel to this side, same number of marks, which is impossible because we can see them intersecting right there. So that's a bad example. But if we were to draw an actual parallelogram, which I'll define in a second, some books include that as being a more special trapezoid. Not this book that we're using this year though. So our definition is a four-sided figure with exactly, I'm going to erase that at least, with exactly 1 pair of parallel sides. So there's a couple examples here. The most traditional kind of looks like this, but you could also have one that looks like this where it's indented. You could even have 2 right angles here, and these being parallel, that would also be a trapezoid. So lots of different examples, right? Once you have the 2 parallel sides, it doesn't matter whether lines are going in, up, out, right? How you connect these, as long as you only have those 2 parallel sides, any version of that is a trapezoid. Okay, definition of a kite, a quadrilateral with 2 distinct, that means separate, unique pairs of consecutive, congruent angles. Oh my gosh, I said angles, I meant sides, that was a typo. I apologize for that. So 2 distinct, so that's here's 1 pair of consecutive, meaning one right after the other, and congruent, meaning they're equal. You can see that from the marks. And then here's the other pair, right? So it means if we have a 4-sided figure, it means we have 1 pair of sides next to each other that are congruent, and also we have the other pair of sides, right? Totally separate pairs. Okay. These are not kites. This one because it has a 5th side. This one because it just has 3 that are congruent and nothing known about the other. This one is not a kite because it's actually got all 4. These are not 2 separate pairs. This is all 4 sides congruent. And then this last one is opposite sides are congruent, not consecutive sides. So again, some books, again, I'm just giving you a bigger picture of geometry. Some books actually define this with at least 2 pairs of consecutive congruent. So actually this could be a special kite in some books, but not in this book. In this book, it is not a kite. A kite is not a rhombus, okay? All right, so down here, definition of a parallelogram. A quadrilateral with 2 pairs of parallel sides. Obviously, 2 sides that intersect at the corner cannot be parallel, so it is implied that the 2 pairs of sides that are parallel have to be the opposite sides. Oh, that was weird. I erased them and they didn't disappear. Okay? But the opposite sides are parallel because those are the only sides that don't intersect. So if you have those 2 pairs of opposite sides being parallel, then you have a parallelogram, right? So we have 2 examples drawn there. And then over here we have a hexagon. That is not a quadrilateral, so that's not a parallelogram. This one is a trapezoid because it has 1 pair of parallel sides. And this other one is nothing. It doesn't have any parallel sides, just a generic quadrilateral. Okay. Now, definition of a rhombus. This is that one up here. This was a rhombus here, all 4 sides congruent. So we could just write it succinctly as equilateral quadrilateral. That means 4 sides, and then all sides congruent. Right, so over here, all this extra information doesn't matter. As long as we have the 4 sides are congruent, then it's a rhombus. Same thing in the next picture. We see all 4 sides are congruent, and there are 4 sides in the polygon. Great. Over here, we have one pair is congruent, and the other pair congruent. That is not a rhombus. That's, in general, just a parallelogram. Again, stuff we'll investigate later. This is just a parallelogram. This one is equilateral, but it is not 4-sided. It's an equilateral pentagon, so none of those are rhombuses, okay? All right, let's go down to the next one. Definition of a rectangle. So really you got 2 different definitions. I mean, the most succinct to me is equiangular quadrilateral. So we've got 4 sides, and then we've got all angles congruent. But then you kind of have to know that for all the angles to be congruent, and if all the angles add up to 360, dividing by 4, again, stuff we'll investigate in more detail later, being 4-sided and equiangular means that it has to have 4 right angles. So these are both the same definition. Either way, it's 4 sides with 4 right angles or 4 sides with all angles the same. And so down here, we have one example of both, right? We have one example where it just shows the 4 angles are congruent, and then we have one example that just shows we have 4 right angles, right? And then because it's 4-sided with 4 congruent angles, then it's a rectangle. Over here, this is a triangle. This is a parallelogram, but we don't know if it's a rectangle. We don't know if the angles are 90 degrees or equal. And then this one over here has opposite pairs of angles congruent, but we don't know that all the angles are congruent. So this one's just a parallelogram. That's something we'll prove later. All right, let's go to the next page. The definition of a square. So one way is to use the word regular. So that's both, that's all sides and angles congruent, and then quadrilateral, 4 sides. Or another way to think about it is it's just a quadrilateral that's both a rectangle, so that means all angles the same, and rhombus, all sides the same. So if it's both all sides and angles the same, then it's a square. So here we have a picture with all sides the same and all angles the same, so that's a square. Same thing here, we have side and angle, side and angle, side and angle, side and angle. All 4 sides and angles are the same. This one over here is just a rhombus. This one over here is just a rectangle. And this one over here is a triangle, so it's not even a quadrilateral. Okay, so those are our special shapes. I just want to quickly review from a different aspect, okay? So I often find lines of symmetry to be super useful in talking about special quadrilaterals. So if you cut a quadrilateral down the midpoints of 2 opposite sides and you get exactly one line of symmetry this way, then this is an isosceles trapezoid. So in other words, a trapezoid where the top side is parallel to the bottom side, but you get this symmetry left to right. And then this ends up telling you tons of useful information, like these angles are the same, these angles are the same, these sides are the same. Obviously, half of the top side is the same as the other half because you have to cut it through the midpoint for it to be a line of symmetry. So obviously these portions, but then you also even get these other results like the 2 diagonals end up being the same. Because when you swing that around mirror image, those intersect here, and you end up getting this piece is the same as this piece, and then 1, 2, 3, 4, 5 is the same as this. So when you add up the 2 same segments with the 2 same segments, they're the same. So many properties fall out of this. Over here, if you cut this down and you have, again, one line of symmetry like this, then this one ends up being a kite. And you can see that right here by saying, okay, well, this side's the same as this one's the same as this because of the line of symmetry. But then you get all this other stuff, like this angle's the same as this angle's the same as this angle's the same as this one. You could even cut it across the diagonal, and this angle's the same as this. The only 2 angles that are the same and add up to 180 are 90, so you actually get right angles. So much of this just comes from the fact that you have this one big, juicy line of symmetry right down the middle. Oh, that was a terrible line of symmetry. right? And I could do the same big juicy line down the middle here. Okay, so the next one, what if instead of one line of symmetry, what if we had two lines of symmetry, but through the middles of the side like this and like this? If you have two lines of symmetry like that, then this is a rectangle, and all the properties shake out. I won't go through the long list. And if you have two lines of symmetry across the diagonals, like this, then instead of it being a kite, so here's two lines. Oh my gosh, this side, so bad. Then this is a rhombus. Okay, and again, so many properties come out of this, right? You have this right here being the same as this because of the vertical line of symmetry. Then because of the horizontal line of symmetry, you get these are the same. Then this one's the same as this one, which is the same as this one and this one. Again, you get this angle's the same as this one. So the same and add to 180 means they must be like this. You also get all these sides. So you get so many interesting things, right? Same here, you get all of these sides the same. Because of that line of symmetry, just like up here, you get that the two diagonals are the same. Not only are they the same, but they're split perfectly in half. So you actually get that all of these half diagonals are the same, which becomes pretty useful. All right, and then finally, if you have a shape like this, which has all four lines of symmetry, so you have the diagonals like a kite or like a rhombus, and then you also have these ones across the midpoints of the sides like an isosceles trapezoid or a rectangle, then this is a square. And it can just help you find all of the properties of these shapes if you're ever confused. So I just wanted to bring that up, and then we're going to just do some practice problems. Okay, now we're going to do some problems down here, okay? So based on the marks, what can you assume to be true in each of these? Yeah, so this is just a quadrilateral. We don't have a special name for this. Okay, we do know it has one right angle. And we do know it has one pair. Whoa, I wrote one pair pretty crazy. We do know it has one pair of parallel or congruent sides. So we could say side AD is congruent to side BC, but it's still just a generic quadrilateral. Okay, so the next one, look at this. So we have one pair of congruent and consecutive sides and a separate, different, distinct pair of consecutive congruent sides. So this one's a kite. We also know it's a quadrilateral, right? Just more generally, quadrilateral. And then we could say those two pairs of sides are congruent. So we could write EF is congruent to FG. We could write that EH is congruent to HG, right? So we're just stating what the symbols say. In the next one, based on what we know now, you probably don't have enough information to say anything more than it's a quadrilateral. However, as we get on to the next chapter and the next unit, we'll actually find that doing a 90-degree turn and another 90-degree turn, that's a 180-degree turn. So whatever direction you were going in here, you're now going in exactly the same direction, but reverse. So these lines are actually parallel because of those two 90-degree angles. That's more advanced. That's not something we know yet in this first chapter. But just to lay it out there, we could actually, with future knowledge, say this is actually a trapezoid. And then we could label the parallel sides and the right angles. Okay, and in the next one, we do know this is a parallelogram, right? Just by the very definition of a parallelogram. And it's also a quadrilateral. Whoa, on the side of my iPad over here, my hand's off the screen, so my writing gets much sloppier as I move from left to right. Okay, so this one says match the term on the left with this figure. Well, let's just go by the picture. So this one is a parallelogram. So let's put that here. That's A. Okay, B is a trapezoid. So we got B. Okay, we can see by the one pair of parallel sides. So C has two pairs of consecutive, and they're different, right? The 2 marks and the 2 marks and the 3 and the 3. So that's a kite with a consecutive congruent side. So that's C. D has all 4 sides are the same. That's a rhombus. So that's 3 is D. E is just a quadrilateral. We know nothing about it, and there's no quadrilateral listed, so we're not going to use E. And F says we've got 4 angles that are all the same, and so that is a rectangle, so that's F. over here. All right, now we need to sketch and label figures. So we've got trapezoid, zoid. So when I draw a trapezoid, I'm going to draw it this time just as like a pretty classic, staple of the genre kind of trapezoid. So here's 7. Now, when you label this, zoid has to go around either clockwise or counterclockwise in order. You can't just be like Z and then O and then I and then D. That would connect like this, and that would not be a polygon. That would be 2 separate triangles, right? So we have to go around either clockwise or counterclockwise. So I'm going to wait until they tell me which sides are parallel. So it says ZO is parallel, so here's ZO. Classic mistake would then be it's parallel to ID, putting an ID here. But again, that would not be trapezoid zoid. That would be ZODI in order around. And so we need to erase that and actually put it in the correct order as we go around the shape. That's ID. Okay, and then down below we kite, BIMF. Okay, so let's go to number 8. So I'm going to draw a pretty classic kite here, and it says BE and EN are the same. So let's do, this is B to E, and that's E to N. That means these two must be the same for it to be a kite. And then going in order, B, E, N, F. So that means the F is over here, and the order is correct. Okay. Let's do number 9. So rhombus. So a rhombus just has all sides congruent, and it says equal with diagonals EU. So that means here's EU going to, and so let's go Q and L. So that's equal, and so it says diagonal E to U. So let's connect it, and diagonal QL. Let's connect it. Intersect at point A. So here's point A. All right, and last one, rectangle. So that means we're going to have 4 90-degree angles. So I'm just going to draw them as right angles, okay? And RGHT with diagonals RH. So I'm going around the shape like this, and it says RH and other diagonal GT. Intersecting at point I. All right, couple more. So draw a hexagon with exactly 2 outside diagonals. So a hexagon has 6 sides, and we want diagonals to be outside. So the classic hexagon would be like this, but then all diagonals would be on the inside. So instead, I'm going to try doing just 1 point going in, right? So it's still got 6 sides, and now one diagonal would be, now let's make it go in a little bit further, okay? So let's erase that. We'll go, so let's see, this diagonal and this diagonal are now outside, but this diagonal not. So let's draw all the diagonals in a different color. Okay, diagonal 1, diagonal 2, diagonal 3, diagonal 4, and diagonal 5. And those are all the diagonals, and that's exactly 2 of them right here lying on the outside. Okay, draw a rectangle. The next one, this was 11. A regular quadrilateral. Oh, so if it's regular for 12, that means all sides are the same and all angles are the same. What is another name for this? This is a square. Okay, for exercises 20 to 23, sketch and carefully label the figure, mark the congruent parts. Okay, hexagon with exactly 1 line of reflectional symmetry. So 20, I'm going to start with the line of symmetry, and we want 3 sides on each, or we could have the side on the bottom. So 1 line of symmetry, I'm going to do something crazy, like here's 1, here's, I don't know, 2, and here's 3, right? And then here's, so this and this and this would be congruent to the other side. So here's 1, 2, 3. Whoops, this should have 3 at the bottom. So there's that hexagon. So 3 sides on each side of the line of symmetry, and I purposely made it so you couldn't do a line of symmetry this way. It was kind of my logic there. Okay, and 21, 2 different equilateral pentagons with perimeter 25. So we could have this one with a 5 on each. That's a equilateral, all sides the same. But then I could just like flatten the tip. Let's imagine these are like toothpicks connected end to end, like it's a jingly jangly little toothpick shape. So I'm just going to push down the point, and so I get those 2 5s on the side opening up a little bit more, and these 5s being stuck in a little more. So they're all still 5. I just pushed the point down a little bit, right? Or I could pull the top up a little bit, and I could get it to be a little more narrow like this. Whoa, that bottom wasn't 5 anymore, sorry. Let's erase that and do that again. So we still have the 5 on the bottom, but then it just kind of stands up taller like this. Whoa, man, off that side, my writing gets so much worse. Okay, that was it, you guys. I hope you enjoyed that first video on special quadrilaterals.